Okay, we're going to cover the last half of Unit 1. So this is 1.6 through 1.10. 1.6 is over describing distribution of quantitative variable. So when we are describing the distribution of a quantitative variable, we are still looking at that acronym SOCV. SOCV. So I'm going to break apart this acronym again, and we are looking at what we're going to find in each of these. So for S, we know S is shape. Okay. For shape, we are going to look for if it's symmetric. And if it's symmetric, then we can label this as either uniform, unimodal, or bimodal. So the different types of symmetry is uniform. And the graph for uniform would look like a rectangle. Okay, all the values are the same. Then we have unimodal, and that's where we have symmetry with only one major hump. So it looks something like this. And then lastly, we have bimodal, where we have two significant humps. Oops. Trying to draw this the best I can. Oh no. Okay. And if it's not symmetric, then the other thing we're looking for is if it's skewed in any way. So our first checking, is it symmetric? Now we're checking if it's skewed. So there's two different types of skew. We have left skew, which is another way of saying negative skewness. And that is where the tail is longer on the left side. So the tail is longer on the left. And that looks something like this. So let's say this is our data chart, and we have majority of our data on the right, and then it kind of just tails off on the left. So this is left skew. Okay. Or we have right skew, or in other words, positive skewness. Okay. This is where the tail is longer on the right. So it's going to look opposite of this graph. We have majority of our data on the left, and then as we go to the right, we have the tail. So this is right skew. And note, this is our data. This is our data. Okay. Okay. So if we are looking at our positive skew versus our negative skew, so our right skew versus our left skew, we know that where the graph is starting to curve down or curve up, depending on which one we're looking for. So right here where it's starting to go up, and right here where it's starting to go down, this is the median. So right here and right here, this is the median. And then on let's see, this is the left one. So right here, right before that is going to be the mean. And then right after that on the right side is going to be the mean. And then on the opposite side is going to be the mode. Okay. So a mode, or in other words called a peak, and I should have drew these modes a little better. So that's the peak. So it's the very top of those distributions. So a mode, or in other words a peak, represents the most frequent value or values in a distribution. So it's the most frequent values. In a histogram, stem plot, dot plot, or other graphical representations of data, the mode is often indicated by the peak or peaks in distribution. So in several graphs, we find the mode by finding the peak. Okay. So that means if we are unimodal, there's one mode. If it's bimodal, it's two modes. If it's multi-modal, then there is more than one mode. And if it's uniform, there's no modes. Okay. So that was shape. Now looking at O, which is for outliers. Okay. Outliers are values in a data set that are significantly different from the majority of other values. They can be either extremely high or extremely low, and they have a significant impact on the measures such as the mean, median, and range. Okay, so it is extreme values which have an impact on mean, median, and mode. Okay, there's several ways to identify outliers. If we were looking at a graph, okay, the outliers would be visible by a data point that is extremely far away. So data point, extreme distance. Okay, so for example, if we were looking at like a scatter plot, right? Here's our chart here. We have our scatter plot where that looks like it's all going in like the positive direction. And then we have this one dot way out in the extreme. That is our outlier. Okay. Another way is if we were looking at a dot plot. Okay. Let's say we had a bunch of points and then one point way over here. Okay. This is called a cluster of data. This point, since it has an extreme distance, this is an outlier. Okay. So we can view it by a graph, and we can also view it by gaps in data. So this is a gap. Okay. And then center, remember we mentioned center, C for center, as the mean, median, and mode. Okay. The mean is often considered the best measure of central tendency for symmetric distributions because it takes into account all the values in the data set and reflects the overall trend in data. So this one is best for symmetric. The median is the middle value in the data set. When the values are ordered from least to greatest, it is often considered a better measure for skewed distributions. Best for skewed. The mode is the value that occurs most frequently in the data set. In a symmetric distribution, mean, median, mode are often close to each other or even equal, depending on the shape. However, in skewed distributions with outliers, the mean, median, and mode can be significantly different from each other. So for symmetric, all similar. For skewed, we have different values. Okay, and then we have V for variability. And there's 3 ways to find variability. We can find it from the range. And the range, remember, is maximum minus minimum. We can find it from standard deviation. And standard deviation measures the separation in data set around the mean. It's calculated by taking the square root of the variance, which is the average of all the squared differences between each value in the data set. The standard deviation is a useful measure for symmetric distributions because it takes into account the entire trend. So I am going to write down the formula. Give me one moment. Okay, so standard deviation, the formula. So before I do that, standard deviation, like I said before, is the distance from the mean. And it's best for symmetric. The formula to calculate standard deviation is equal to the square root of the summation of xi, so our value, minus x bar, which is our mean, squared, over n minus 1. Okay, so n is the number of data points. Xi is the individual values, and x bar is the mean of xi. Okay, so if we were to take all the xi's and find the average of it. Okay. And then the last method to find variability is the IQR method, which is called the interquartile range. Okay. So we calculate this by subtracting the first quartile from the third quartile. So Q3 minus Q1. The first quartile is the value that divides the bottom 25% from the top 25%, while the third quartile is the value that divides the bottom 75% from the top 25%. It's often used to describe the spread of skewed distributions. Okay, so right here it is best for skewed. Okay. Okay, 1.7. 1.7 is the summary statistics for quantitative variables. Okay. So this is when we were talking about that 5-number summary for box plots. So what I'm going to do here is I'm just going to reiterate the SOCV. So you're going to hear that a lot, pretty much all throughout the course, but a lot in Unit 1. So statistical center. There are several ones, which you should know by now, which is mean or medium. And the mean is better for symmetric. And then we have median, which is better for skewed. Okay. So if we're determining which one we would choose for the center, you want to look at the ones that are symmetric, then you would use the mean. If we had any type of skewedness or had outliers that could affect the mean, then you would refer to the median. Okay. Statistical variability. Okay. There are two things that we talked about here. So that was standard deviation versus IQR. So standard deviation, when you think of this, I want you to think of it as the lungs in statistics. You cannot breathe without it. You cannot analyze data without it. It shows how far or how close the values are from the mean. Okay. When we calculate standard deviation, we won't always be using the formula mentioned above. I'm going to show you guys later how to do that on your calculator so you don't have to take up so much time finding standard deviation. The IQR, or the interquartile range, is based on the difference between the upper and lower quartiles. Okay. If we were deciding which one is best to use, if we had a symmetric distribution, which means that the mean and median are approximately equal, and the standard deviation in IQR is approximately equal, it's best to use standard deviation. So for standard deviation, we are going to look at symmetric distributions. And if we had any skewed distributions, we would use IQR. Okay? And remember, in IQR, we can use the method 1.5 times IQR, so 1.5 IQR, to determine outliers. Okay. And based off this, we know that a outlier is one that is greater than Q3 plus 1.5 IQR, or less than Q1 minus 1.5 IQR. Okay? If we have any data points that meet that criteria, then it's called an outlier. Let's look at 1.8. 1.8 is the graphical representation of summary statistics. So this brings us back to when we learned about box plots. Okay? So a 5-number summary provides the summary of the data set. It consists of the minimum value, the first quartile, the median, the third quartile, and the maximum. Okay, so it's the minimum, Q1, the median, Q3, and the maximum. This is a 5-number summary. A box plot shows a 5-number summary the best. Because if we remember a box plot here, we had our box right here and then right here. Okay. So at this point was our minimum, and this point was our maximum. This whole thing is our IQR, where the middle line is the median, and then this is our Q1, Q3. Okay. These things on the side between our minimum and our IQR, this is called a whisker. Same with over here. This is a whisker. And then if we had any outliers, they would be beyond the maximum and minimum values. Box plots can help us find important features about the distribution. The central box stretches from Q1 to Q3 and shows the middle 50% of the data. When we are looking at a box plot, we should also consider the whiskers. If the whiskers have different lengths, the distribution will be skewed on the longer whiskers side. So whiskers, if have different length, then we know that the distribution is skewed on the longer whiskers side. To determine if whether a box plot is skewed or symmetric, we can also look at the position of the median in relation to the first and third quartiles. So let's say we had one that looks like this. So here's the whisker, here's our quartile, and here's a shorter whisker. This one is left skewed. And then we have a shorter whisker, our quartile, and then a longer whisker here. This one is right skewed. And if the whiskers are about the same length, then there's no skew. Okay, if you look on Schoology, I do have a couple practice examples and the answers if you want to look through that, and that is on the Unit 1 overview, one variable data PDF. But I'm just trying to get through just some notes. So let's look at 1.9. So comparing distributions, quantitative variables. So looking at this section, it's best to describe the notes by showing some examples. So the first example says the weight of two groups of 8 animals, group M and group N, are recorded and the data is shown in stem plots. Use the stem plots to compare the weight of the animals in the two groups. Okay, so I'm going to do group M. Here's the stem plot. So we have 1, 2, 3, 4, 5, 4, 3, 4, 8, 2, 6, 8, nothing on the 4, and then 0. And then group N, I have 1, 2, 3, 4, 5, 6, 0, 3, 6, 5, 1, 4, 7, 2. So in order to compare the groups, we have to look at the distribution of the data and compare the range of data. From the stem plot, we can see that group M has weights ranging from 14 to 50. So range for group M, 50 minus 14. While group N has weights ranging from 10 to 62. So range 62 minus 10. Group N has a wider range of weights, with some animals being significantly heavier than any heavy animal in group M. So if we were to calculate that, I would have 50 minus 14, 36, and 62 minus 10, 52. So that means group N has heavier animals. We can also look at the distribution of data within each group to see if there's any patterns. If we look at group M, we notice that it has a cluster of values in the 20s and 30s, right here. While group N has a more even distribution of values. This suggests that group M has a higher proportion of animals with similar weight. So, based on clusters in data, group M has animals with similar weights. Overall, the stem plot shows that group N has a wider range compared to group M and a more diverse distribution, since group M has a cluster of data with animals with similar weights. Okay, so that was us describing the data from the stem plot. If you look at, again, back to that PDF, there's 2 more examples with the answers if you want to go through them and see if you can get them correct. And then lastly, we have topic 1.10, which is normal distribution. Okay. In normal distribution, we learn about z-scores. So z-scores, which is also known as a standard score, is a measure of how many standard deviations a data point is from the mean. So how many standard deviations from the mean. Okay, And we use the formula z is equal to xi minus x bar divided by standard deviation. Okay, remember xi is any data point, x bar is the mean, and SD is standard deviation. Z-scores are useful for comparing values within a data set and for determining whether a value is unusual or extreme. They can also be used to standardize data for comparison between different data sets. So since z-scores are called standard scores or standardized values, we can have negative z-scores and positive z-scores. So negative z-scores. A negative z-score means that the data value is below the mean. And positive z-scores means that it is above the mean, data above the mean. Okay. The further away we are from the mean, the more unusual the value is. So the further we are from the mean means the more unusual the data point is. Okay. Okay, so here are some examples of normal distribution. These examples include height, IQ scores, blood pressure, and income. But there's several different types of examples. Those are just a few. And then we have two different types of normal distribution. We have the normal model which we use for symmetric distributions. And then we have the standard normal model, which is shaped like a bell curve, where the mean is equal to 0 and the standard deviation is equal to 1. To check if our data is symmetric, it's common to look at the histogram of data to create a normal probability plot. A histogram should show a roughly symmetric distribution with a single peak in the middle. Okay. So if we had a histogram here with different amount of bins, we could use that to create our standard normal model by saying this looks similar to the bell curve. We can also use the imperial rule, which is the 68, 95, 99.7 rule. For normal distribution, 68% of observations are within one standard deviation. So 68% is within one standard deviation. 95% is within 2 standard deviations, and 99.7% is within 3 standard deviations. And I have a diagram of that rule on Schoology to better illustrate what I'm talking about. And then there's also practice problems at the end with the answers if you want to try those and see if you get it correct.